Hello, everybody. We are the Bionic tires, and these are our design and build tutorials. Specifically today, we're going to be talking about some of the essential mechanisms, some stuff that will be very useful for you when you're designing your robot as to what it should do on the game. So the first thing we're going to talk about is the fundamentals of any robot, which is your drivetrain, which is the wheels that your robot will be based on. There are a few different variations that we will go over. The ones that we will be talking about will be the 4-wheel drivetrain, the 6-wheel drivetrain, the Mechanum drivetrain, the X-Drive drivetrain, the Hdrive, the treads, and the swerve drive.
Drive train constraints are some things you got to think about when you are designing your drivetrain. Things you want to consider is your top speed, so how fast your robot can go. Acceleration is similar. Your power, your maneuverability, traction, terrain, omnidirectional, and cost. So the terrain is you're good.
One of the kinds of drivetrains that we were talking about earlier is the 4-wheel drivetrain. There are a few different variations of this. The 3 configurations that we have in this that we have to talk about today are the 4 traction wheels. Those are these bigger wheels in the back. They only can go in one direction. It's got good traction, but it doesn't maneuver that well. The second configuration is the 2 traction and 2 omni. That is using these 2 omni wheels. And what omni wheels are they are thinner wheels that have rollers on the sides of them so that they can move around the axis of rotation around where the motor is, but also they can slide side to side. And if you have 2 traction and 2 omni wheels, then your center of rotation won't be in the center of your robot. It will actually be in the center of your 2 traction wheels. And it will have better traction than some drivetrains, but it's also got some decent maneuverability. On the other side of the spectrum, there is the 4 omni wheel drivetrain, where your drivetrain is consisting entirely of those omni wheels, it is very maneuverable. Your center of rotation is directly in the center of your robot, and it has like a turning radius right on a dime, but it slides around very easily and can be pushed by just about anything. Good thing about these drivetrains, though, is that they're very low cost, especially. All they take is 4 motors and 4 wheels. And these are some of the different variations. So earlier was the 2 traction, 2 omni variation. These are the 4 omni variation. And this is 6-wheel.
Another variation of a drivetrain is the 6-wheel. It's pretty similar to the 4-wheel. Things it can do better is it can climb up some obstacles better, especially if there's if your 2 wheels on the outside are not close together. And it's pretty much the same amount of speed. Some cons is it's larger, it's more expensive because you have the 2 extra wheels, and it cannot strafe, unlike the 4-wheel drivetrain.
Next up, this is definitely the most common drivetrain in FTC. It's the drivetrain that our team uses and has used for the past few years, and we find it very effective. This is the Mechanum drivetrain. So if you'll notice, they use these 4 wheels that are technically allow for omnidirectional movement, but they're different than the omni wheels that we were talking about earlier. As you can see, they have these rollers that are configured at a 45-degree angle to the axis of rotation that the wheels are turning along. And that can be used if you drive those wheels against each other. Those rollers will actually slide the robot along the direction that those rollers are facing. And you can get strafing or side-to-side movement, but you still retain a decent amount of traction. So good things about these, it's only 4 wheels, 4 motors, high maneuverability, pretty decent traction. Unfortunately, it only works really on a flat field, and it is much more complicated to program than something like the 4-wheel drivetrain or even the 6-wheel drivetrain. And it's pretty expensive because, especially if you get higher quality Mechanum wheels, they can run up in price pretty quickly.
The X-Drive is also decently similar to the Mechanum drive because it can strafe. It can pretty much go in all directions you want. It can go. It's a little bit cheaper because you don't have the Mechanum wheels. They're just for Omni wheels. But this is not very common because the wheels on the corners are a little bit bit space consuming, and it's a little awkward to mount, and it's roughly the same complexity to program.
Next up, we have Hdrive, which is similar to our X-Drive and our Mechanum drive, can strafe, which is good, which improves maneuverability. But one of the biggest cons that you're going to have with this configuration, and one of the reasons why it's very uncommon, and I don't think our team has ever used it, is the fact that you're going to be burning 5 of your motor slots when you're only allowed to have 8 motors maximum on your robot using 2 control hubs. So you're using 5 of them on your drivetrain where you could otherwise use 4 on something like an X-Drive or a Mechanum drive. But it is easier to program than something like a Mechanum drive or even an X-Drive. But it's just things to consider. It also takes up a lot of your building space right in the center of your robot where you just can't put anything there because it's being used up. And it has about the same traction as that 4-wheel Omni drive that we were talking about earlier, and the X-Drive, which isn't great, but isn't too terrible either.
A drive with treads is not the best drivetrain out there because it has poor maneuverability. It's it's very expensive, and it's just not very good.
Swerve drive, this is definitely one of the most complicated of the drivetrains and also one of the least common. That doesn't mean that it's a bad option. When it's implemented, it is one of the best drivetrains that I've seen work effectively, but it's very difficult to pull off. So that's probably going to be more of an off-season project that you don't want to chew up a bunch of your time with. But it is really great in maneuvering because, as you can see on the picture over here, the basic premise of it is that there's 4 of these caster wheels, which are not omnidirectional wheels, which you would think would take away from maneuverability, but they actually have these 4 servo motors attached to each of these wheels that can change the direction that they're facing. And that allows you to move in just about any direction you want because you just pivot the motors, and then once you run the wheels, the robot will go in whatever direction you need it to. It's definitely more complicated to program than a 4-wheel drive, and it's probably going to be even more difficult than a Mechanum drive or an X-Drive, just because there are very few resources online that will tell you what to do, especially compared to those other common strafing drivetrains. It also uses 4 servos in addition to those 4 motors. We were talking earlier on the Hdrive about how you want to pick an efficient method that uses the lowest amount of motors. Servos aren't really as valuable. We don't usually come terribly close to our servo limit, but it's just something to keep in mind that you are using 4 of your servo slots on your drivetrain. And again, you do get more than 8 servos, but it is just something to think about. Yeah.
There's drivetrain methods, which is how you get your motor to your wheel. So different examples is the direct drive, the chain drive, and belt and gear drive.
So we're going to start off with something that is going to be universal for pretty much any drive method, and that is a gear ratio. This is very beneficial if you know how to take advantage of it. And it is also something that if you aren't planning on having it come into account, is something that you're going to have to think about, because in any system that you make where you go from your motor to whatever you're going to, there is likely going to be a gear ratio, even if you don't think that there is going to be. So the definition of it is changing the speed and torque of a system through differing diameters between the driving and driven components. For example, driving component may be your motor and your driven component may be your wheel. Some ways that you can change your gear ratio is motor, gearbox, drive method, which we're going to talk about in a little bit, or even the diameter of your wheels as they touch the ground, which is the one that gets overlooked a lot by people when they're making drivetrains or other mechanisms. Over here on the right, we have a simple diagram that shows your driving component, which is twice as big as your driven component, which means that you have a 1-to-2 gear ratio, which means that this driving component is going to turn once for every 2 times this driven component can turn. So this driven component will be twice as fast, will have half the torque, and conversely, this driving component will be half as fast, but it will have twice the torque. And again, this can be accomplished through a whole bunch of different ways. And even when you're just direct drive a robot, there you also still get a gear ratio from the size of your wheels, and that will be something that you'll have to take into account.
So another example is the chain drive. You get a little bit more you get more flexibility where you place your motors, because you get the chain from the wheel to the motor, so you can put those motors in the middle or something, and then you're able to also adjust the gear ratio. But the chain requires some tension if you don't get the chain links perfectly together, the links also stretch over time, and there also is multiple points of failure.
And just something to note real fast about chains and chain stretch. Chain stretch is something that in a lot of times in our past cases we've kind of discounted, but what happens is the individual links will wear a little bit, but over a long chain that compounds. So you just have to keep that in mind and make sure that you have a tensioning system that you can adjust to account for all of that. Next up, we have direct drive, which is by far the simplest driving method. If you didn't know anything about driving methods, it's probably just what you would do. You would just take your motor, put on some structure, and then attach whatever you're driving on the end of that. So for example, right here, you can see this motor that is going directly into this traction wheel. Very few points of failure, but unfortunately, it does put stress directly from that wheel onto the shaft, which then puts stress on the motor's gearbox, which could cause some problems later down the line with how your motors are behaving. Also, you can't do a gear ratio. So if you have a 435 RPM motor, your output is going to be 435 rotations. And that's just how it is.
The boat drive is very similar to the chain drive, because you're taking your motor, which you can be flexible with the position, and your output's going to be the wheel. And so yeah, it's very similar to the chain. It's a lot lighter. There's less backlash. There's fewer points of failure, and you can also do the gear ratios like you can on the chains. These require precise attention to get it to work right, and they are also a bit more expensive than the chain drive.
All right, next up we have gear drives, which is where the term gear ratio comes from. So you do get some flexibility on where your motor position is if you're using gears, but not quite as much with chain or with a belt. They still have to be relatively close to each other. Also, they can be susceptible to grinding and slipping, especially if you're doing fancier gears like angled gears or beveled gears when you get away from spur gears. And it's 2 points of failure, which is similar to a lot of the other driving methods, but it's just something to think about. And when you're in a confined structure like a U channel, as you can see in our example right here, you can't get like a terribly large gear ratio because you'll run into the edges of that channel. And you won't have the space to design for something like that.
So some tips and tricks are here's some advice for advice based on our own learning. So D-shaped and hex shafts are probably the best shafts to do when you're constructing your robot, because there's a lot less chance of there being shafts and shaft collar slipping and stuff. Using consistent structure such as channel pieces is very helpful. CAD and prototyping before making complicated assemblies can also go a long way, so you can isolate all those risks you got to take. And then planning your drivetrain to accommodate the other mechanisms on your robot is also very helpful.
All right, now we're going to talk about the game process a little bit, which will get us into some of our other mechanisms. In every game that you're going to have to play, and no matter what the rules are, it's always going to involve some sort of obtaining a game element that you are going to then transfer with the mechanism to get it into the position that you need it to, and then you are going to score the element. That is, regardless of whatever the rules are in every FTC game, there is some element of obtaining something, transferring it, and changing where it is in your robot, and then scoring it. Those are the three things that are going to remain constant across any FTC game.
So obtaining elements is normally the first part of your scoring. So you're scoring. You're just scoring. So first thing you got to consider is the element type, which will manipulate the what you're actually grabbing or getting the elements with, which could be grabbers, overhead spinnings, dual side spinnings, or a passive intake.
And those are used to pick up the game elements that we talked about earlier. There's a few different kinds of game elements that First likes to use. In this upcoming game, we're going to be using these spheres and cubes, which were also used a few years ago on the Rover Ruckus game. But there's also some other things like rings that were used last year, or a whole bunch of other things like these donuts, or really whatever, or the blocks from Skystone, or really whatever first things that they want to use.
So some collection considerations is the reliability of the thing. Like, you don't really want something to be not very reliable. Minimal lineup. You don't want to take your time lining up your robot to get the to intake your elements. You want it to be very fast, versatile, and you want to consider the size and shape of the game elements.
Grippers are one of our first examples of a way of getting these elements into your robot. Some pros of grippers is that you can design them around basically any element that you'd like to. Like in this bottom picture, you can see that that's a 3D printed piece that it fits exactly around that relic. But unfortunately, it does require a good amount of lineup, probably the most out of any of the ones that we're going to talk about. And it's also a very time-consuming collective process, because you have to collect around 1 or 2 at a time, and you can't just keep on feeding them into your robot. So you can only pick up one. Your claw can only obtain 1 or 2 elements for every cycle that you open and close it, which is not the most efficient way of doing things, but it is fairly easy and simple to design.
Overhead spinning is a very good way to intake stuff depending on the situation. So they are a fast collection. They take very little lineup. They are reliable for cubes and spheres, and they always continuously collecting. But usually with the overhead spinnings, they take up at least like one side of your robot, and they need lots of material testing to find the right tension.
Similar to overhead spinning, there's also dual side spinning, which is good for things like compliant wheels, where you can see in the bottom, which is good for anything that really has more of an unusual shape, or cubes, because cubes have a flat side that the wheels can really get a good grip on. They're fast, they're reliable, and they're continuous, which are three really good things for collections. You can start it running. There's not a lot of lineup. You just go over to whatever you need to go over to, and it will just suck it up into your robot. There's a little bit of lineup, but there is not a whole bunch of it. These are something that we have used frequently in the past for fast games and have gotten a lot of success out of.
So the passive intake, some examples are the scoops, forks, cups, and some pros are they are very simple to design, but cons is they need to line up really. They really require lining up, and they're not very versatile.
Now that you've collected the element, you need to transfer it into a position that is where you want the scoring element to be for when you score it. And there you can use certain mechanisms such as the single bar, the chain bar, the 4-bar linkage, or the linear slides, which we will get into shortly. So something that first is very famous for is they will almost always require you to take a scoring element from a lower position to a higher position, whether that's shooting it up into a higher position or lifting it with slides up into a higher position. They almost will always have like a lower goal that you can get into without lifting, and then a higher goal for way more points where you have to lift things. And that's why a lot of these mechanisms involve getting the element from in your robot to a higher position on the field.
So some lift considerations is stability. You don't want something to be too tall and not stable. The heights, which is important to reaching some of those elements, are the scoring zones. The speed of your lift, the balance of your robot. You don't want one side to be like way too heavier than the other, and the combination of different lifts.
So one of the more simple of lifts is a single bar. It's all it is just a lever that you put on your robot. So you can lift it up, you put the fulcrum right where your motor is, and you drive it so that when it's down, the lever is touching the floor. The end of the lever is touching the floor. You put whatever your load is onto it using one of the collection mechanisms, and then you can run the motor, which will rotate the lever up, and that will bring your load, which will have your elements that you're going to be scoring on, up to whatever goal that you're scoring into.
Another example of a lift is the chain bar. Is very simple, and it maintains the orientation of the element, but it can be it cannot be too long due to the leverage of the chain. We don't want like the chain to snap in the middle.
Next up, there's a 4-bar linkage. And this is like, it's good. It's similar to the chain bar because it will keep the same orientation. So if you're picking whatever you're picking up, if it starts off level to the ground, it will end up level to the ground once you have it all the way up. It is kind of complex though. There are some opportunities for more complexity, depending on what you need it to. So it's pretty adaptable. You can either do a regular 4-bar linkage, or you can do a 6-bar linkage, or you can do a double reverse 4-bar linkage. They all have different use cases, and really you can adapt it however you want to.
Linear slides is another example. It can, some pros is they are extremely common, and they are very space friendly. They all like collapse into the generally the same area. The cons is they can be very complex, and you will have to move your robot around it to get the lift line up in the same area. And some methods to do the actual lift of the slide is the string. You can do belts and chains, or you can do a lead screw. But it's you need to make sure that your robot is evenly balanced, so your robot does not tip over when they are lifting up heavier elements.
Which is the same for a lot of these different types of lifts. Whenever you're lifting any large amount of weight, which you may not think that you are. If you have like a really light game element, you might not think that you're moving a lot of weight, but you're also moving all of the parts of your lift. So like on a cascading lift like this, all of the individual stages of that slide are going up with your element. The same with your linkage or your chain bar. So you just have to make sure that you have a heavy enough drive base that when you lift all of this stuff up in the air, and you start to go forward, that your inertia doesn't carry you over and tip you over, which is something that a mistake that we've made very often. So that's about a wrap on our essential mechanisms tutorial. Hopefully this is something that you found useful. If you have any questions about any of the mechanisms that we showed or any of the things that we talked about, feel free to reach out to us. We will be happy to talk to you. Or if you want some advice on how to implement these better. We also have a couple other tutorials in this series, a couple on the business side and one more on the build side if you'd like to check those out. You can also look into the FTC Discord or the FTC Reddit, and I'm sure that they would be more than happy to answer some of the questions that you have. Thank you for tuning in.